The variance, you just square and then multiply, right? That gives you the expected value of x squared, which is 9.2. And then sigma squared is 9.2 minus 2.6. You could use the usual formula, but then it's a mess because 2.8 is not in. So the last problem suppose 100 spins result in 62 floors to decide the general probability of at least 62 floors in 100 spins. You only expect about 40, you've got 62. So it's probability x is very equal to 62, which is 1 minus probability x. And then that probability is binomial, right? N to 100, you have to recognize that. And P is 0.4, that's the probability of success. So then use this notation, P binom, okay, the notation is given at the top up here, right? 61, 100, 40. That's the answer, right? That's the answer I know. Any questions on that? So I assume you would have it if you were on R. Then we can count. A lot of you didn't have to do that. Six odd numbers spun in 10 spins, exactly 6, right? So here n is 10, and success is still 0.4, it's an odd number. Success is 0.4, probability of success is 0.4, and then it's go out to 6 and subtract off out to 5. Again, almost all packages have this. Of course, if you use D, that's for the point mass. So that's fine. Again, you didn't have to. This is fine. Four is Poisson, right? Lambda is equal to 6. And, no problem. Determine the probability of close to 12, so that would be less than or equal to 12, right? And mean is 6, so that's the answer. P voice. Oh, 9 or more would be the complement of less than or equal to 8. So that would be 1 minus P voice 8. It's a little bit different. It's a combination problem, right? You have a great month and you sell 14 houses. Find the probability of 3 successful months out of the next 5. That's a binomial, right? N is equal to 5. And P is the probability of success. So it would be that. 1 minus P voice 13.6, right? It's 14 or more. So this would be the probability of success. And then it's just P binom. N's 5, and this is P. out to 3. This should be out to 2, so the difference would be exactly 3. See, this is the beauty of R because this is simple in R. Right? When did I say you don't do it? You can do this. Oh, so you could just put the probability in with no date.
D3.
Let's get that next. Close to 0.
D.
Any questions on the quiz now? Yes, you did very well. Yes.
What's the D? Is it?
D is the point mass. Probability at that.
Oh, okay.
Probability of success is really minus up. Yeah, it's 3 out of 1,000. Second 100-year flight. You sell 14 houses. It's like the 100-year flight. You're going to be excited. Okay, questions on exercises? Let's do the one with the car. We have our method. Okay, so far we have one method. We have this binomial. Population. Bernoulli. That's right. Which was unknown. Now we're back in the world of statistics. And, so you take a sample, right? One height is success and 0 is failure. And then our p hat is actually just a sample average, which we always write as just x bar, right? Although in this problem we use p hat, we wouldn't use x bar. P hat is the usual notation. Okay, so this will be our estimate, right? When the sample comes in, and I switch the little x's in, right? But I don't have a little p. Use x bar. This would be our estimate of p, right? And then the standard error of the estimate is the estimate of the standard deviation, right? And then we have a confidence interval, it's just p hat plus or minus the z critical point times the standard. Well, so now we have a method, and now we have a problem. We have this counter at the intersection, and you want to see if you should, they need a left turn signal. And so what they do is they, you see these counters all the time, they just wire across the road. It keeps track of whether it turns left or right. Goes straight. They have a light, he probably has radar on it or whatever. So, well, now they come, I have a camera up there and they watch it. I'm on that SAMDOT study. I'm just consulting this guy's station. It's like they have cameras on some important intersections in Michigan. Spent a few minutes watching the camera. Okay, but anyways, getting back to our problem. So here's the data.
Is this in problems or in
Yeah, there's a thing on exercises.
Is it number 12?
Yeah. Are you with me on assignments now? You look at the assignment, and I'll try to say, I look at these problems.
You changed it since the beginning of the semester.
Oh, yeah, right, everything's live, sorry.
Oops. I think that's not one problem. Okay.
Fastest, yeah. Profit. So we want to just count the number of go left. Right? I think there's 60 observations, so out of 60, we just have to count the okay. So there's 2, 3, 4, 5, 6, 7, 8. 8. So our estimate is 8 over 60. So that's calculate our estimate. Let's get a decimal for that. It's not bad on that too. You have to do it here. So p hat 8 over 60, right? So it's 2 over 15. I'll just call it p hat. You know, you can just do this on your calculator, right? It's 0.1333. So it's at least 3 places. And then we want our confidence interval or the standard error. The standard error would be this, right? And maybe 1 minus that. And down to 60. So then we calculate that. Let's call it SE for standard error, right? So our standard error is point. We're going to have one design the same confidence. fourth. Vote for, vote for four. Okay, and now we can do our confidence interval. We have to pick up. Now we have to select the confidence. Let's be a good government person. We'll select 95%. So then the critical value is 1.96. And so here's our CI. 0.123, right? Plus minus. So that's half made for my confidence interval, right? So it goes from 0.047, right, to 2.1. So I'm very confident that the proportion of people that turn left at this intersection over this time period, et cetera, you might have a few clauses or phrases in there to modify what's going on. It's between 0.047 and you're talking to your boss, you might shorten it to 5% to 0.2%. What's he going to say? Let me give that answer. Any questions on the method? So we're set on that, right? So what's your boss going to say? You can't get any better than that.
Yeah. Just give me one number.
Well,
That's what he'll say.
yeah, that boss is the 0% confidence.
Mm-hmm.
So you just come back and say 13%. I ran a consulting several years. I get to that point. Sometimes. Well, what I'm looking for is the margin of error is too much, so you could try to reduce it. And this confidence interval is very nice because with it we can actually come up with sample size determination very quickly. That's a big thing as a staff consultant. You're always asked, what should the sample size be? And then you try to pinpoint it. It may be a very complicated experiment, but sometimes you can come down to like a simple confidence interval, and when they agree on that, you say, great, got it. Immediately. Okay, it might be a complicated experiment, and you might have to go through some calculation. Anymore, computers are so fast, we just do simulations. And this one thing I'm working on in research, I picked out appropriate degrees of freedom for something. And, the other day, it said, oh, we ran 100,000 simulations. We're probably done with it in a few minutes. Just amazing. Okay? But this one is very easy to see. So let's just go back and do that. based on this confidence interval. So you have this population and you want to estimate P, okay? And the statistician is going to ask you within what margin, okay? That's like happening for confidence interval. You have to be careful. Sometimes people think that's the full length, but most of us think that's half. So we need the bound and half length confidence interval. How about this? I'm going to estimate P. So I need that, and I do need alpha. And for a moment, I mean, we can do it, but that's all we need, really. It'll be conservative. But let's set up and let's see what the next one. Okay, so this would be half length, right? And then you just solve for n. So root n is greater than or equal to n. That choosing n. Now, why put this thing up? So let them. And you have the bound, and then you say, well, no, you don't know. I mean, you have the sample size, right? You don't know P, so you can't use it. Well, okay, there's two ways you can go. You can have a guess at P, and in this case we do. It's like a small pilot study. They might have just, instead of putting the wire down, they might have just sent something out to observe. We have to put the wire down. So there's two solutions. This yes, pilot study. Some web information. So in our particular problem, the example we do this because we have P hat. So suppose in the example, your boss would be happy. So our half length is 2 times. Maybe your boss wants it down to 5%. Let's say you can just put that in. Again, everything is in the right place. If you want more precision, you want a smaller b. B is in the denominator. Make the b, make it smaller. It gets bigger, right? Then will get bigger. You want more precision, 99% confidence intervals or anything higher. Then this will be 2.3. Gets bigger. Okay. And then we'll talk about what's inside here in a minute. So now we're going to crank that out. It's 171.7, so we round things. you might say. But, okay, we just leave it at that.
I'm sorry, what is given P hat pivot?
Pilot.
Pilot?
Yeah, that's how you spell it.
Pilot.
Pilot. Pilot.
PIL.
It's given,
Pilot.
oh,
Oh,
pilot study.
Yeah. I forgot.
Excuse me. Oh,
All right,
excuse me. No, in the square root, that's 0.13 and
times.
pi 866. Oh, okay.
That's a parenthesis. Oh, yeah, picky. In fifth grade, I decided I'd write my own way, much to the teacher's dismay. Get some arguments. Finally, we've compromised, and writing fast like we did. Okay, so we have, any questions? Now, the main thing in this problem is you can get a conservative estimate where you don't even know P. Okay? And you luck out in this problem because if you go back to where we were, we have P times Q here. And guess what? That's a quadratic. The graph is a function of P. It's 0 at 0, and it's 0 at 1. And then it is a quadratic. It's upside down. It's P minus P squared. And it'll peak at 1/2. So this is always less than or equal to 1/2 times 1/2. So you can fit that in here. So you're going to be conservative. So the inequality you're going to solve in that is this. You're going to solve that inequality. The other one's back here. You sandwich that in. And then you ignore it, just solve for that. So you do have in this case, you can, this will come out to be this, right? You can generate the square root of 1/4, this is 1/2. So in this particular problem, it would be, and then these almost cancel out, right? If you use alpha equal 0.05, and so this would be 0.05 down here, which is 1/20. It's 20 squared or 400. So it's not, someone could figure it out, but it's about 400. So that's the price you pay, it's conservative. It pays to know something, okay? If you know something, you should use it. Now that has to be you have to have some confidence in that estimate. But you can always go the conservative route, which is sort of neat. This doesn't happen in many other problems. Well, maybe some other proportion. Okay? You set on that then? Okay, so we can even get the sample size determination out of our confidence. Okay, any questions on the confidence?
I have a perhaps silly question. What is our beta representing, or the B rather? It says 0.05, but
You're estimating within 0.05. That's half length of your confidence.
So isn't that
I
alpha?
think that's what people mean when they say within.
well, isn't that what alpha is? How-
Oh, well, that's just a coincidence. That's just a coincidence.
So B is the margin of error
Right,
on both ends.
you're estimating P within. What is N? Okay, so that's what we answered that question. Okay, there's one thing about confidence interval, and that's selecting alpha, right? And I'll say this: if alpha is smaller, you have more precision, but your length of your confidence interval goes down. So, I mean, if alpha is smaller, if the confidence is smaller. If the confidence goes down, precision goes up. So this is alpha gets larger. Alpha goes up in precision. And alpha goes down. Oh, it's just, I'm sorry, I still got factors. Want to be more precise. We go, yeah, that's right. So it's like I'm more precise at 95%. 90%, 99%. Now, on the basis of that, pick out your alpha. It's hard to do, okay? You do a confidence interval, and maybe one thing we'll be looking for is confidence interval that's not in this problem here.
Likelihood of error goes down.
Would be like zeros in the confidence. You should have more than 95% confidence. Some people try to do that. They grow out their confidence interval to catch a zero. It's actually zero sentence. But there's an easier way to think about it, and that's through testing. Testing lets you think about the power and then from that it's clear that sometimes you want to ride with high alphas. Okay. So that's one motivation to get into testing. And the other motivation is a quote from Darwin. The only reason to gather data is to test the statistical hypothesis. So we shouldn't talk about testing. We can motivate it with it. It's some problem here that it's probably talked about in the book. There's a baseball data set, and it looks like there's too many left-handers in it. So it's adult males and professional baseball players. That's very important. Probability of being left-handed for a male is between 10 and 11%. So we look at the status on baseball players and say, oh, there's something wrong. There's too many left-handers. So what you do is you form a hypothesis. And I mean strong hands. In a data set, look strong. I think you throw with your strong hand. I don't know why you throw it. With your weak hand. here's the null. They're just like anyone else. That's the null hypothesis, right? And then this is like the alternative hypotheses. This is like the alternative hypothesis of interest is A, it's over 10%. So this is our second thing of inference, and we'll be using this throughout the class too. We're going to test this hypothesis. Now, when you test a hypothesis, you can make an error. Okay, so what's the test going to be? Well, you're going to observe some data, right? And in this case, you probably take p hat. Well, if you want to keep it separate, at least for a little bit, that has to be the number of successes. Now, most of our hypothesis testing will be very intuitive. We're not going to do mass stat in this class. Mass stat will tell you the decision rule you should pick. But in most cases, it will be very intuitive, so we won't even have to think of it. We go with it and we reject. We're going to reject H naught, favor of HA, see if S is too low. Under H naught, we expect S to be n times 0.10. So n is like, well, we could use the data set. The data set has 59. If n is 59, then under H naught, we expect S to be about 6. So if it's around 6, I'm not going to reject. It's going to have to be up here. So that's when I reject, right? If S is over K. If you expect 6 and you see 7, I'm sure you're not going to go out and reject. Some people might. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, etc. Where do you draw the line? Okay. There's only 60 observations, say. If you get up to 30, that's 50%. That's most, we talked about this, right? That's most animals. Dogs are 50%. So then you have to determine K. Right? So how do you determine K? How large is too large? Well, we go back to errors we can make, and we focus on one error, and that gives us K. The mass stat people gave us S greater than or equal to K, right? This is from mass stat. So I can't think of another test. Errors. That one is when you reject H naught. And H naught is true. now there's, let's see, the book, that table is in the book. Here's the summary table. From the book, okay? The true state of nature is at the top, H naught is true, well, I guess I'm using H1. There I'm using HA. I always use HA in the mice. H naught is true or HA is true. And then there's your decision, you reject H naught or accept H naught. If you reject H naught and H naught is true, that's a type 1 error. And if you accept H naught but H sub A is true, then that's type 2. Okay? Now you have to make a decision, you cannot sit on the fence. And then once you see that, then you know you can make. It's like the confidence in the book canvas, right? Okay, well then what do? It's type 1 error. We just found the probability of type 1 error. That gives us a test. The test is done. As soon as you give me the alpha for type 1 error, the test is over. So this is the worst error. So then we select alpha. This will be the level of significance. Sometimes it's called the size of the test. And alpha is probably okay. And that sets K. Right? Straightforward now. So in our problem, suppose you set alpha to be what? 5%. So suppose you, in the example, suppose we set alpha equal 0.05, then to determine K, I just put that in, that's probability. And I like to think of this as under H naught, that's where you take the probability for type 1, right? H naught is true. We reject H naught, that's S squared equal to K. Okay, and then from that you can determine K. You can do it two ways. I noticed when I was looking through the book last night that I use finite probabilities. Why don't we just use some Z critical quantities? Because that's what we're going to be doing later. I'm not sure why I do that. Then I just have to make this a Z. Okay. So now I go back to central limit theorem. I have to subtract off the mean and divide by the standard deviation. And that'll be approximate Z. Now I'm going to approximate a binomial with these bars. So this would be the distribution of that. Use K. Okay. So now I'm going to lay a normal curve over this. So I might use a continuity fraction. Right? I might back up to K K minus 1/2. Nothing changes when I do that. Now it's just a standardization problem. We're under H line. P is 10%. N is 59. Okay. And I'm going to standardize this to normal. So I just have to standardize both sides if I want to. But we could do it in general, and we don't have to do it again. This would be P naught, okay? P naught set, here is 10%. We know N too, but why don't we just do it in general? And then I know this, see this is 0.05, and I can just go to the table in the back and look this up. What's the answer? That's how long you've been in statistics. You just fill your head up with all these meaningless things. I'm 0.645, I don't know why.
So 4.9.
No, you would find that in, like on the T table, right? You don't have, I meant to, I do not have a T. And then we have K, right? K is going to be 1.645, or in general, that would be Z alpha, right? So here's our general rule, we even have a general rule, we want to use it. So for our problem, for the example, we can just substitute in. This will be 1.645, and then this will be 59, this will be 10%, this will be 90%, this will be 59, this will be
Who's slide there?
okay, so now I can solve for K, and then I know what K will be. Right? Now, I'll just. So it's 10.19. So we'll probably round. We put the 1/2 in already, so I just do rounding there. This was above 0.5, I would go up. It's below 0.5, so I'll go down. I just take K. So I'm going to reject H naught. K is going to. I mean, yes, that's. So now we're ready to test. It's a 5% test, and we're ready to go. So we just go out and look at the data, and then we'll decide from our data whether we inject H9 or not. Okay. So how much bigger does it have to be above 5.9? It has to be 10 or more. So, data. I just clicked on data on 566.
1.96, right?
This is Carrie's baseball data.
Yeah.
This is having the fastest years. It's Carrie's baseball data set. Carrie, my daughter, was 6 years old. One day I noticed she had a pack of 59 baseball cards. I don't know where she got them. She said later on she traded them for some Barbie balls. Found them in a trade. So, Carrie hates baseball. Anyways, one day I was actually babysitting Carrie, and I took the data off the cards, and it's a very interesting data set. It's simple, it's straightforward to understand. This is the height of the baseball player. This guy comes in at 6'7", and he weighs 232 pounds. And then this is how he bats. Left-hander, switcher. And then this fifth column is how, I don't have the definition here. I think the fifth column is how he throws. No, the fourth column, this column. This column is his hand. 1 if he's right-handed. No, 1 if he's left-handed, and 0 if he's right-handed. This fourth column, right? The fifth column is a pitch hitter indicator. And if it's a pitcher, like this guy, his earned run average is 3.38. And if it's a hitter like this guy, his batting average is 2.34. Okay? Anyways, we're only looking at the fourth column today. You can see that there are very few left-handers, okay? But there are 15 of them. There are 15 left-handers in that data set out of 59. So we definitely inject H9. So we go back to the data here. So we can inject the 5%. So we would inject H9, and then we would claim that P is over 10%. In this data set. Now, if you know anything about baseball, you know why that's true. If you think about it. We can talk about that later. But at the moment, we get rejected. Okay? We have a few minutes left, so why don't we just push the p-value today, and then we'll come back and talk about the power of the test tomorrow, next Tuesday. So we have not talked about what's missing in our great conversation. Why didn't you set alpha to be 0.01? Why don't you set alpha to be 10%? Okay. So there's a we have to come back to this type 2. Look at power. That might clarify this opposite. Remember, the test was given to us once we determine the probability of type 1. It's done. You give me another alpha, I have another K. Now, but one thing, actually, what we'll do in practice, so what do we do in practice? We go back to this example. So what do we do in practice? Well, we know our problem. And we should formulate our hypotheses. If you don't have hypotheses, you're probably into estimation and confidence levels and things like that. And that's important too. But quite often, or very often, you have hypotheses in your mind. This is my thesis. Right? I know what should happen, of course. Yeah. Oh, I didn't know that. So just you know. Okay. See, it's like it's in confidence intervals you don't know this. And then what else? Well, you don't select a level. Page. Yeah, here's S. This is the whole thing right here. There's the hypothesis testing problem. Here's the background of the problem. The hypotheses of interest is usually the alternative, not always, but usually. It certainly is in this case, right? And here's your statistic of interest. This is your test statistic of interest. You'll know that, okay? Or you might have to look it up. And then you'll know when you're going to reject if S is too large. That's what you'll know, okay? And then you just let the data come in. And in a sense, you sort of like estimate how large is large. You estimate the significance level, all right, at which the test would reject. We rejected at 5%, but we only had to get over 10. We got to 15, okay? It's more significant, right? It's like we didn't have to get to 15, we just had to get to 10. Okay, so then you observe the data. Okay, so then you get S. And then you calculate the probability, and we'll call it rho S, not the standard deviation. We calculate this probability, the probability under H naught, with n equal to n equal to 59 in this case, where it is. And, it's under H naught, so P naught would be the probability of success. C is what we observe. So this is the observed value of the test statistic. I'll write this way. Okay. That's how far out we got. It's like, think of S as the observed K. And then we calculate this probability. Okay? And this will give us the level of significance at which we would reject. Okay, we can reject down that far. Okay? This is the observed significance level. This is the lowest level at which the data rejects H1. Very rich. So you can calculate this. This would be a probability that this binomial. This will be what, 15, and then you subtract off. It's still calculated under H naught. So again, you might use a continuity fraction. Then you would subtract off the mean. It's under H naught. And you divide by the standard deviation under H naught. Everything's done under H naught. And then you have to calculate that answer. It comes out to this is 3.73. And see, that's the beauty of z-scores. So it's like we never use them anymore to calculate probabilities, but they're still useful. You know you're out in no man's land, right? You just observed, if H naught is true, you just observed a z-critical value of 3.7. 3.7 standard deviations. 0, right? That's pretty odd. And the probability of that occurring is it's 9.4 times 10 to the minus 5. So it's pretty odd. It's 9 out of 100,000 times. Not the lotto, but it's kind of low. The lotto is like 117. No, it depends on the lotto. So that would be the observed symptoms. Okay. Any questions on that? So that's what's really done in practice. Most of the time, you know your hypotheses, you know where you're going to reject in a sense. You know the rule, like in general. F squared equals k, whatever. Then you let the data come in, and then from the data you decide. That's what the statistician really has to do, okay? The statistician cannot set the alpha for the person. Setting the alpha, and we have to talk about power. Again, we're back to setting alpha, right? So we'll talk a little bit about power next time. But, that's the statistician doesn't want to set alpha for the client. The client has to set alpha. Okay? How significant do you want to be? If going from H naught to HA takes a lot of money, you probably want a very low alpha. You've got to be sure. Okay. But if you're working in a laboratory and you're looking at discoveries, no, you're not gonna. You're gonna let the alpha ride up soon, right? Because you're gonna come back and look at it anyways. So that's why there's not a set rule. Okay, so we're on our way. What goes next time? It's Tuesday. No, it's Thursday. So we'll talk about the power of the test a little bit next time, and then we'll get into, we'll embed this problem into the one sample discrete problem.